Thank you. Thanks, David. Thank you for the invitation to speak here. So I'm going to speak about some recent work. So I think I mentioned some work I've done with my PhD student about the sort of the limit of the hyperparameter, and then the current work with my colleague from Berlin, Natalia about the actually the BVM type result. So see, there we are. So I just give a quick introduction, more sort of to set up the notation. Then actually I gave the outline already. As I said, the adaptation that I've done with we've done with my student Genova Rodriguez, and then the Bernstein-von Mises type theorem with Spokojny, and then I'll show how it works on simulations. So this is the general setup for linear inverse problems. So you're interested in some function or in f, but you don't have direct observations. So perhaps it's a tomography, or maybe noisy, like blurred image, or some integral or differential operator. And then we assume that it's observed with some Gaussian noise. So sigma here is going to be my noise parameter. So if this model is equivalent to the finite dimensional sort of approximation or with n observations, if we set sigma equal to 1 over n. So if we think about the rate of convergence or contraction or something like that, so it just think that sigma is 1 over root n. So in this setting, when W is the white noise and sigma is like this, then it's a white noise model. If I have to, so that's the model I'm going to focus most of the time, although I'll be mostly speaking in sequence space. But at the end, I'll also discuss briefly how my student and I, we considered it for colored noise W, and also the case when the prior and the operator are not necessarily simultaneously diagonalizable. So how we can still and when can discuss this setup in the sequence space. Okay, so the simple way to go into the sequence space is to look at the singular value decomposition of this indirect operator. So for integral and differential operators, that used to tend to be straightforward. If it's tomography, it's radon transform. Again, this is sort of known, and the rate of decay of A sort of determines how ill-posed the inverse problem is, right? So so here we have, then the idea is to decompose F in the appropriate this one of the eigenbases. And then if we then transfer F applying operator A, then we in the basis of the other Hilbert space with the basis V. So then we can decompose Y, the observation, into that space, and that because of the orthogonality of these bases, it leads us to the sequence space, right? So we have, this is the decomposition of the original data in the eigenbases. These are the eigenvalues, effectively, of the, well, singular values of the operator, and F is part of the decomposition of the original function F in this eigenbasis, right? And we assume, well, if it's a white noise, then, and this is orthonormal basis in L2, there is no issue. The decomposition, we can apply, effectively integrate the white noise with any orthonormal basis, and we get the IID sort of standard normal random variables. And if sigma is constant, so it's just white noise sequence space model, right? I goes 1 to infinity. So this is the sort of the model I'm going to work with. So the interest is to estimate F, right? So we have some sort of ill-posedness. I'll focus on the mildly ill-posed problems, although the results we have applied to, we can apply them to severely ill-posed problems as well. So we assume for the moment, so at least we assumed with my student, that the distribution of the data is correctly specified. So the data comes from, indeed, from the A with some true function F star, and the distribution is normal and have the correct noise. Later on with Spokojny, the idea is then to apply this to misspecified models where this assumption does not necessarily hold. So we assume so for the mildly ill-posed problem, we assume that f comes from the generalized Sobolev spaces. So that relates to the basis. So effectively, we decompose f in the basis that is arising from the operator A, and we assume the coefficients in that basis sort of belongs to this generalized Sobolev space. So for other types of spaces, for instance, analytic functions or the general results, instead of I beta, we can use the other sequences just increasing, and that would lead to other sets of function spaces. Okay, so prior, if we have the information that, particularly if we look at the posterior contraction rates for the functions over the Sobolev spaces, then the prior choice of prior tends to be matching to that, so to the sequence we have. So it is the sort of sequences, just we don't know beta, right? So we put the prior for f is normal. Again, I think there is some work by Sergio Agapiou and Peter Mateo when they talk about putting informative prior here, but I think that I'm not sure if it works with adaptation though. So without any prior information, put mean 0, and then some scale nu that I'm going to focus on later on for adaptation, and then we assume they're decaying at some polynomial in I with sort of some parameter alpha, right? So I have two parameters. Alpha is the sort of prior smoothness, and nu is some sort of scale parameter, right? Sort of like the radius of the ball here, the analog of that. And in particular, one of the interpretation of that, so with probability 1, this S, the Sobolev alpha dash norm of f is less than infinity for any alpha dash less than alpha, right? So it does describe smoothness, a priori smoothness assumption. So the aim is to estimate the posterior distribution of f and adaptively to known beta. So that was our original aim with the student. So so just maybe a quick review of, sorry, I'll stand here. So the posterior contraction rate. So effectively, we look at some distance between the function we estimate and the true function. So I'm going to use the L2 norm here. And we want to show that it decreases, so it goes, well, consistent, and then consistent at a particular rate. So of course, it's sort of non-unique, but effectively, we try to find the largest to which it does go to 0, right? So it tends to be, the minimax rate tends to be a reasonable benchmark for that. So in the practical tool, in fact, for L2 space, it's really straightforward. There is barely any sort of difference with the frequencies, which you just take the, you're using Markov inequality, take the expected value of this quantity squared, sort of divide by this, right? And as long as we show that this is bounded, well, actually, so it goes to infinity, goes to 0, sorry, sigma goes to 0, right, the noise, then we have the posterior contraction rate. So, so if this is infinite dimensional setting, so sure if, there is some work about the sort of Bernstein-von Mises sum result for f. However, here we're going to more focus on the functionals of f, which are finite dimensional. And we'd be interested then in the frequentist coverage of these posterior credible regions. And then if this variance is the correct one, so the Fisher information for Q of f, then we can say that Bayesian inference actually is valid, right, for inference. It's not just some posterior uncertainty. Okay, so just to the benchmark. So for the Sobolev spaces and mildly ill-posed inverse problems, so beta is the sort of unknown smoothness, p is the level of ill-posedness, the minimax rate is known, and it's sort of, you can remember sigma squared is 1 over n, so it's approximately n to the power minus 2 beta over 2 beta plus 2p plus 1, right? So that's going to be our benchmark. Just a quick overview of different ways to adapt. So one of them, sort of a discrete one, is so ideally, if we didn't have any noise, we just take our data, divide. Remember the setup. And just go back to the linear set. Right. So here, if we didn't have any noise, so what we do is just take y divided by I as f. Right. So here, the way it's done, it's the same way. We just take this, but only up to a certain level j, right? And then to go back to f, we just plug in these coefficients into the basis. And the oracle value, so that is, if you knew beta, well, and even f star, then the oracle value is of this order, so it's n to the power 1 over 2 beta plus 2p plus 1, right? And there is a nice sort of way to do it adaptively in the Bayesian setting.
So j naught is the same as j.
Yeah, so sorry, yes, so j equals to j naught. Yes, you're right. Sorry, yeah. So you would, yeah. So would you would use that sort of, yeah. I don't want to go into the Bayesian model, but yeah, yeah. Right. So the other one is regularization using. So if we fix the scale, but we try to estimate alpha, right? So somehow plug in the value of alpha, that would lead to the optimal, sorry, I'm in the frequentist setting now. So optimal convergence rate of the estimator. So effectively, then we plug in, yeah, sorry, 0 here is sort of like the oracle, yeah. So we plug in the value of alpha into this truncation. It's sort of like ridge regression type coefficient, right? We plug in the true smoothness here, and that would give us the minimax rate. So remember, A here is from the inverse problem. So sigma is the noise rate, and J is the sort of regularization, right? You can think of this as the this is sort of J inverse here, right? Sort of the variance. Right. So in that case, so if we put alpha equal to, oops, sorry, I'm running. Alpha equal to beta, then this would get the minimax rate. So this is the benchmark for this approach. For the in the Bayesian setting, this was done by Ard and the colleagues. But it only works for f that are the subclass of function f, true functions f. I'll discuss that later, so it doesn't work for all of them. So this works for any function. So the third way to set up well, there are probably more, but 3 of the most commonly used one is to fix alpha and to estimate this scale parameter nu. Then the benchmark is sort of n to the power minus this. So alpha is the wrong smoothness, but this scale sort of adjusts for that, right? So there is a difference alpha minus beta. And it works as long as alpha is greater than beta, but also minus 1. This was done in the, before us, it was done in the Bayesian setting for the direct problem by, again, Botton, Szabo, Ard, sorry, I think it was Harry van Zanten. I can't quite remember the third colleague. So they've done it for the direct case, and we've done that for the inverse problems case. So it does work for all true function f star. So whilst we were proving that, so we were estimating the parameter, and we found interesting properties of nu. So we've done it in the empirical based way. So for the direct problem, it was done for Botton, Ard, and Harry. So I think they approached, so I think if we apply our results to the approach, it sort of worked. And the PhD student was just focusing on finishing his PhD, so he didn't, we didn't go into the details of the full posterior, but the preliminary results, all for the empirical base, all that they had, we have. So I think it wouldn't. It should be applying, but anyway, we haven't done that. So we focus on just the empirical base posterior and estimate nu hat by using the marginal maximum likelihood approach. So let me run through that. So effectively, we integrate out f. And then what we have is new, just one-dimensional parameter given all the data. And then, sorry, should be maximum. And then we've effectively maximized the marginal likelihood here. And then when we look at the posterior distribution of f, we just plug in that value. So, I think some people consider also prior new. So in that, sorry, should be maximum again. And then it's maximizing effectively the posterior distribution of nu. So the key is sort of what are the frequentist properties? What can we say about that? So that's based on our paper published in Scandinavian Journal of Statistics. So we focus on alpha greater than beta minus half when it is possible to adapt. So this is just a reminder for the likelihood of the prior. So this is the inverse problem in the sequence space. This is the prior. Alpha is fixed. Nu we're estimating. Right, so what we showed that if alpha is greater than beta minus a half, then the marginal MLE is actually bounded above by the sort of the oracle value. I should probably put nu naught, the one that we've seen in the review of different methods. So by up to a constant that depends on alpha and beta effectively. And so in particular, remember there was also the dimension that was important, so it's, if you go up to that dimension, then there is called a critical dimension, then you're recovering your signal. You can go above, you're still okay, but if you go below, then you get a non-trivial bias, right? So in this case, so this critical dimension with this plug-in parameter nu is also bounded above by a J star, but I think so, and then posterior distribution contracts to the point mass at f star at an optimal rate. So the reason that it is upper bound and that's sufficient, I think, because if we assume that f is in as beta star, we don't know if it's like actually beta, right? So if we say function is like 3 times differentiable, in fact, it may be like 5 times differentiable, right? So in fact, even though your posterior contraction rate can be faster, but it's certainly bounded above by whatever the beta equals 3. That's why if you don't know sort of whether f is on the, what they call the boundary of the smoothness, then the upper bound tends to be sufficient. I mean, there is a lower bound as well, which is important too. So, and in that case, we do have that the posterior rate of contraction, I sort of didn't worry about the constant here too much, but we have the specific constant here, behaves at the, it's an sort of posterior contracts at the optimal rate if we plug in this estimator with high probability. Right, so this adaptation method does work, but also, we can do uniform adaptation if we bound beta by beta, some sort of value beta naught, and then we choose alpha from the priors beta naught minus 1, and then our assumption that alpha is always greater than beta minus 1 sort of automatically holds, right? So, if you have any questions. Okay, so what happens in the other case? So when alpha is less than beta minus a half, what we found is that nu is bounded by power of sigma or n, which doesn't depend on beta. So therefore, we cannot adapt to the smoothness. So Judith and Botton have general theory for optimal posterior contraction using full empirical Bayes approach, which is nice for interpretation. We tried to apply it, but I think they have an assumption, for instance, f has to be stronger assumptions that we have. I think Halder and I think some Bowden does. So, which I think the results would be similar. Right. So what we also found, we were interested because sometimes we had the lower bound on nu hat that was of the same order, and sometimes it was different. And it turns out for those self-similar functions for which when we tried to estimate beta and we using the that approach of odds are bottomed and so on. So it only works for this set of functions. They refer to them as self-similar, though they looked at the Hölder space, but this is the sort of Sobolev analog. So effectively, you want to say that it's not just that the beta is the sort of the upper bound on the smoothness of the function, right? Because normally we have just up. So this condition is we have upper bound on the as beta known, but we also have some sort of lower bound. So if we take beta dash greater than beta, then then we may not necessarily have the upper bound, but we have also so the way we formulated it, this is has a lower bound in terms of this norm, but it's sort of scaled by the power of n, depending as far as we go. So effectively, for the rates, we just needed, so if we take the prior alpha, remember that was possibly greater than beta, then we need a lower bound on this sum. And to have the matching order, that sort of condition is the one we need. So here C naught is some number between 0 and 1, and it will feature, so when we look at the posterior concentration of this parameter. So if for this set of functions, so for this condition, this effectively for f to be away from 0, otherwise nu hat is just, nu is going to be close to 0, and it's just doesn't quite, just a bit of a different behavior. You get the parametric rate, obviously, for f being 0 and so on. So this is just for f to be away from 0. In that case, we have the exact convergence of nu hat to the oracle value. And then it's not just the upper bound on the critical dimension, but they are approximately equal. Right, so once we got that result, well, so if we were in a frequentist setting, if we have a parameter, we'd start thinking, well, can we find its distribution? So that's exactly what we started to think with Volodya. So this is the setting, and the sort of what we started thinking, Volodya suggested, well, the nu is a positive parameter, right? So why don't we take the logarithm and see if, and look at that. So that would be, see if it can be approximated by the normal distribution. For the case when the nu hat concentrates, i.e. for the subsets of functions from the Sobolev space, we take alpha is this beta naught minus half, or the other way around. If we fix alpha, it means we can adapt uniformly for beta and 0 to alpha plus half, right? So, okay, so then the next task is to study the local concentration of this posterior distribution of the log nu. Okay, so there are, so this is just to remind the setup. So instead of nu, now I have e to the power kappa here, right? Alpha is still fixed. So if I look at the margin, just apply the same approach, but now for kappa rather than nu, effectively running through that and plugging in the this polynomial values, we have that the marginal likelihood for kappa is sort of normal, but 0 mean in this variance, whereas the true distribution of the data, sorry, large marginal likelihood for y given kappa, right? But the true distribution is different. So we have model misspecification. So the first question we had was, will the posterior distribution be of the right order? Right, so that was the first question we addressed. So yeah, so under this condition, and particularly so we start with just non-informative prior, so effectively looking at the marginal MLE or uniform prior for kappa. It turned out to be sufficient, just running ahead a bit. Right, so what we want to show is the posterior distribution of kappa given all the data is normal. So the best possible way this delta will have the sandwich variance, right? So because here we have in the misspecified model, we have Fisher information, which is the variance of the score function. But also what we have is the local curvature of the expected likelihood, and that's exactly the posterior precision. and they may or may not match, right? So we hoped that they would match at least in order. We sort of expect that the exact exact match is sort of not very likely, right? So kappa star here is the effectively the Kullback-Leibler minimize of the Kullback-Leibler distance between this model and the true model, right? So, or we can write it as the, sorry, it's Volodya's notation, with non-trivial. So L is the log likelihood here, the capital L. Okay. So yeah, sorry, L is the marginal log likelihood. So this is an infinite dimensional setting. So we just take the Radon-Nikodym derivative of the posterior with respect to this product of the normal zero sigmas, right? And then it's well defined. Okay, so the critical dimension here, I'm probably going maybe into too much, but for this particular sequence is quite easy to write. It's sort of, it's like a particular power of kappa. And then we can show that for this model, the critical dimension corresponding to the minimize of the Kullback-Leibler divergence has an upper bound. So that's without any additional assumption on F star, just that it belongs to the Sobolev space, has an upper bound which up to a constant is the oracle value for the for this problem, right? So which implies at least that the posterior distribution contracts. Sort of that's what we had before, right? Because of the one-to-one correspondence. So not surprising. And what we have also that we have the lower bound on the critical dimension. And here we have it in terms of this C0 constant that appears in the lower bound here. So you see the otherwise, apart from this error, right? So it's to the negative power, so it's okay. So this is the main factor that separates the two bounds, because for large, so J star increases when n increases or sigma goes to 0. So this is of order 1, but it's this factor that are responsible for the mismatch in lower bounds. So if C0 is close to 1, then they are very similar. If it's C0 is closer to 0, then there is a stronger mismatch. All right, and the constant, all the constants we have are specific. So we see beta, I think it's either 2 beta, 1 over 2 beta, I just can't remember, but it's, so B here, if you're interested in, again, constants, is a beta function, and A is known to a statistician, so it's the prior to alpha plus 1 plus the opposedness to P, right? Okay, so we have the critical dimension is of the right order for this problem. I just wanted to show you the log likelihood that we're approximating by the Gaussian. So it's not surprisingly if you've seen the sort of the adaptation. So if problems, so for smaller value of kappa or nu, so the non-informative to the likelihood, then around the critical value, it's sort of locally quadratic, as we'd hoped, and then it sort of decays in a pretty much linear manner. So this is the log likelihood, right? So we just need to make sure we're close enough, and all this, the smoothness, sorry, the curvature here is positive. So it wasn't particularly straightforward to study because it's not a positive value. So we do have in the end the sort of the probably D not, I should call it just D star or D. So it's the same D squared. So the posterior variance has this form, and we can show that it's positive, but only if C not that lower bound in the self-similarity here is large enough. So for C naught is greater than 8 over 27, it worked. I think if it's a little bit smaller than that, I think 8 over 81 to 8 over 81, 8 over 81 to this one. So we have to have constraints on alpha. So, but for this one, there are no constraints on alpha. Effectively, just to make sure, it may be just the tools we're using, but I tried really hard, so I couldn't do this any better if anyone. but I cannot show that it's some sort of critical bound. So, but anyway, that's what we have. So that the posterior precision for this problem for nu B is of order the critical dimension, right? And we have pretty much, well, they're not the non-matching bounds are sort of because of the C0 value again. Otherwise, it's sort of half of well, this is a little bit. So anyway, they are sort of close to each other. It's up to constant, but they are of order G star, right? So then the next question would be to find the Fisher information, see if it's of the same order. Let me just to have a look to show you the posterior distribution. So if we write the posterior distribution in terms of the log likelihood, right, as the standard trick, we subtract L of the oracle values, well, the minimizer, rather, we just happen to be almost the oracle value. And then we do the quadratic approximation here, or sort of almost quadratic. Then we need, so we separate the expected value that we've studied and the stochastic term. And so this is effectively minus d squared that we studied. This is quadratic. This is a small term that will bound. And then we have the stochastic term. So this is the derivative. Sorry, this is the score, again, that we studied. This is the just local behavior of the score in this neighborhood. And then we'll need the large deviation. So just to say that the large deviation, I think there's, just one slide where the likelihood is flat. I'm just, what I'm looking for is a particular cutoff, so I can say, for kappa or whatever, the parameter greater than that, it works, because otherwise it's non-integrable, right? I can't just leave that, or I'll need a prior for that case. So the upper large deviation on the other side is fine. So that's why I'm only going to give the local results without going into large deviations. So we have that the posterior, I should have said posterior precision, so it's of order the critical dimension. Turns out that the higher derivatives roughly all of the same order. So if we evaluate them at the critical value here, then it's a critical dimension. For other values that we need for the fourth derivative, it's that plus whatever the critical dimension corresponding to that parameter. If it's smaller than the critical one, then we have the upper bound. Otherwise, we'll just have to keep that. But we are in the local neighborhood, so it's not too bad. Okay, so if we just plug this in, so for on this interval, so for in this neighborhood, so if we have some sort of large radius, but r over the square root of the critical dimension is small, then we have the local quadratic approximation, right? And yeah, so this will give us condition on R. Okay, so then the stochastic bounds for the variance, again, we have the upper and lower bounds of order J star. So this sort of one of the constants is the matching, but we have the additional on the upper bound, which I think has a trivial lower bound. So, and that gives us the effectively, well, we can have the probability bounds as well, and also for the difference. So just to say, they are all in terms of either the square root of the critical dimension, or perhaps the maximum if kappa is bigger than kappa star, which locally, again, we can handle. Just to say that the bounds we have with Volodya are all non-asymptotics, and although sometimes I follow the constant, sometimes I don't, but they are relatively simple and straightforward, if that's important. Okay, so let me now formulate the local approximation of the posterior distributions, just a reminder of the model that we have. So just kappa is this log of the scale parameter. So effectively, if we have alpha greater than beta minus a half, and function is not just from Sobolev, but also self-similar with this lower bound on this C0 squared value. So then we have the approximation. So at the moment, you see I cut off, I'm not going to the minus infinity for this parameter because otherwise it wouldn't work. But as long as we are above some constant, then we can approximate the distribution of posterior distribution of kappa by the Gaussian one, right? So here I just recentered and rescaled the kappa and then approximated by the normal distribution. And then the errors, so this comes from the approximation, the local quadratic approximation and the stochastic terms, whereas this one comes from the upper tail here in the large deviation. So effectively for any r greater of whatever, for instance, square root of log, well, greater than that, right? So square root of log j star, and as long as not too large, so we have the posterior contraction. Okay, just to say the cost of having a larger alpha, effectively you need to have a larger sample size. So if you had n beta samples that would allow you to reach a particular posterior contraction rate, then to achieve that for a larger alpha, the cost is sort of n beta what we had before, but also n, the previous n, but to the power like twice alpha minus beta, and rescaled by the smoothness and ill-posedness of constant. So it's not sort of, although we do have adaptation, so in principle you can think, oh, why don't we choose alpha like a million, right, or something like that, and just that we always have, it will always work, but that's the cost. So let me see. Yes, so this discrepancy. Remember that the both posterior precision and efficient information are of the same order, but I just wanted to see how they differ. So this is a particular setting when beta is equal 1, and this is see how it depends as a function of a. Remember, a is 2 alpha plus 2p plus 1, right? So effectively, when we take a large alpha, what happens? So it's the constants seem to stabilize. I think there is a 1 over a there. So when a is large enough, it just doesn't seem to matter anymore. So in this particular problem, I think I haven't showed you a setup, but I will in a moment. So it sort of stabilizes in here. It's about 10%. So efficient, effectively, the posterior distribution in these cases. So the variance is smaller, right, than the efficient information. The precision is larger. So let me show you some simulation that we've done with my PhD student. So here he picked Volterra operator, is effectively an integral operator, right? And then his conjugate is easy to look. It's just the first one integral up to x and the other one from x to 1. So if we're in 0, 1. Eigenvalues in the eigenbasis for the range of a, it's of order I to the minus a half, right? And it's sort of easy to write the eigen functions. And then I think the sort of one eigenbasis has signs, and the other one for the other operator has the cosines, right? So it's easy to implement. So he picked this particular coefficients, right, for the true function, and this is the observations for this data and true function f. Right? So I think I picked beta. So I think it's just nearly 2. I think in the way it sort of works for this case. And this is the posterior distribution of kappa with. So I've tried to approximate the non-informative prior. So first I did the normal with the large variance, right? So locally it's almost like a constant, but sort of just to run the MCMC and see what you get. So the red dot, if you can see it, that's the the value around which the posterior concentrates. So it sort of looks, in this case, looks fairly normal. So I think so it's just different alphas, right? So here alpha is 2.2. So remember the true smoothness beta is just effectively any beta for less than 2 works. So this is 2.2 and this is 3, right? So it sort of behaves fine. I think we had the larger values of alpha as well. We needed like much larger sample sizes to actually get to the point that the posterior converges. Okay, sorry, not the posterior converges, but we have actually approximation. So for large alpha, so I think, let me just see so this is n equals 1,000 and this is 100. So it sort of still seemed to be, although not quite as good approximation, but a bit asymmetric. Actually, judging by these results, I was wondering whether it's worth trying not normal, but another approximation, because it seemed to be asymmetric, and it seems from theoretical perspective, you know, it's not a symmetric distribution, right? You wouldn't expect the local, but I mean, the approximation seemed to be working anyway, but that might be a future work. So I've done it also for the uniform distribution minus 100, 1,000, although it's probably too big. But anyway, so these are the distributions centered at this oracle value, and they seem to provide a reasonable fit, although they still look a bit asymmetric. Then I tried different centering. So here it is at the x cup, and here it's just the posterior mean, I think. So probably a bit of a less fit. So here alpha is really large and n is 10,000. So it, which sort of maybe getting a bit small for this large alpha, although here it's a reasonable approximation. So just to show you that the sample size, because it's a power of n, can get quite large so that you need to get before you get to normality. So these are point-wise confidence intervals for each sort of point. So it's not really the confidence band, right? So it's not appropriate. But so the way I think alternatively could just simulate the values. So I think, you know, simulate the trajectories and see if that fits. But so here the point-wise, so they're reasonably sort of almost inside the confidence region for f, right? The true value, right? So so I was wondering. So this was the first sort of step, and try to understand why and how it works. So if we had a finite dimensional theta, right? So rather than going to infinity, but we truncated at some point, right, to some capital N. In that case, if we can use the Laplace approximation, the marginal distribution is I'm just effectively giving the derivation of Judith, Sonia, and Katya. So they said, well, in that case, we can approximate the marginal distribution by the likelihood given theta plugged in theta hat, and theta hat given nu, right? And well, the determinant. And in that case, what they have done, if this maximum of theta given nu is finite, then there is a non-zero variance. And if it's infinite, so then the posterior the empirical posterior is at the point mass. So we have we hope that we'll get a full look at the empirical posterior. So once we plug in and look at the posterior concentration, it has a non-zero variance. And so that's our sort of next problem. I'm not going to talk about it, but just maybe highlight the problems. So if we do that, so if we now look at the posterior distribution of f, then the way this nu hat behaves, it's approximately as if you only go up to the critical dimension. So effectively approximating, or we're approximating the maximum of f star only up to the point j star. So that's what we found. So if we only go up to j star or something like that, then we have the joint distribution, joint Gaussian distribution of f and nu, and it all behaves well. But if obviously we don't know that in advance. But for a general case, we have. Anyway, we have a bit of a problem. I'm not sure how much time I have.
Still 15 minutes.
Okay.
Including questions, ideally, but
yeah. Do you have any questions? what I'll maybe quickly show you is, so what happens if we don't have the white noise, or when we don't use, so here the prior was conjugate, right? So effectively we did a prior in a sequence space. That is, if we go back in the set of space of functions, we effectively looked at the prior distribution on F that's simultaneously a Gaussian, that has the covariance operator that diagonalizes simultaneously with the kernel, right? So with the indirect operator. What happens if that's not the case? So in this paper with Zhinova, we also looked at the inverse problem with colored noise. Sorry, I switched just using the same notation in the paper. So epsilon is now sigma, right? It's still one. When it's small, right, then we have the approximation to the non-parametric setting. Right, so now instead of having the white noise, we have some sort of colored noise. That is, the covariance operator may not be identity, right? And some sort of prior distribution. So typically, people look at the fractional noise limit because it is the limit of the non-parametric setting where the noise is dependent, right? So it's a natural way of modeling that in infinite dimensional setting. And also, well, in both normally, typically both the indirect operator and the covariance operator of the noise, they're given by the problem. So it's unlikely, well, chances are they may not be simultaneously diagonalizable. So effectively, you does not necessarily exist a basis or a like a rotation, right? The
You apply the same when you operate.
Yeah, and then you have everything is diagonal, right? So effectively, the key here, yeah. So both, so it's like, I think it's the same with the matrices, right? So I think if, but this is the operator in infinite dimension. So in finite dimension, it's easier, although not always happens, right? If yeah, but here it's more difficult. Think again, Sergers, Agapio, and Andrew Stewart, they had a paper on that, I mean, a while ago, but they looked at the particular differential operators, and I think they are I mean, they derived the rate, but it was a bit suboptimal, so we've improved on that with our approach. But it seemed to be a problem, particularly of also, oh yeah, I have the, right, so it's been done by Sergio and Andrew a while ago. The rates were a bit suboptimal. Also in econometric problems, apparently they arise when you model sort of infinite dimensional models with instrumental variables and integrate things out, and you get dependence operators. So I think I spoke to Anna about it. So they've tried, they got also suboptimal rates. So what I looked at least by the time we've done it, so only Ian and Bernard done it for modeled this sort of problem with fractional noise, but for direct problems, and studied it theoretically. So the fractional noise was our sort of example in which we run everything, but the setting applies to other operators as well. Right. So the idea is to use the SVD type decomposition, but using wavelet. So, and also I'll sort of, anyway, I'll probably run out of time trying to explain. It's probably, if I explain in detail, a good probably half an hour, but I'll just give you an idea. So how to apply it, it's sort of, the idea comes from wavelets. So think Donahoe and applied to approaches using wavelet, wavelet. So we're generalizing one of them to this, but they applied it to the white noise here. So we're effectively generalizing their approach to wavelet. So in both cases, so wavelet, if you're not familiar, is a wavelet to which an operator is applied, right? So it's sort of like wavelet, but it's not. Right, so but has some properties, and then to retain orthonormality, effectively they use a biorthogonal transform. So you, right, so in one direction you use one set of functions in the, and then to go back it's a different set. But then in the actual sequence space you get independence and diagonalizability. So it doesn't all work for all of the operators, but it does work for some. Again, I'm not going to talk about that, but in the paper we also we looked a lot at the sort of plug-in estimators in the sequence space. So, for instance, if we don't know exactly the sort of the operator V, or if we don't know A exactly, so we maybe observe them with noise. So we looked at the what conditions we can put on this model when they are known and still get the optimal contraction rate, or the effect of their behavior on the contraction rate. So we also looked, I haven't talked about this at all, but we also looked at severely ill-posed problems and both Sobolev and analytic true functions, because we derived the general rate. And in both cases, we looked at the adaptation to the unknown smoothness. So for mildly ill-posed problems and Sobolev spaces are effectively, it's the same idea. And because it's all in sequence space, it all works the same way. And we've also done it for severely ill-posed and analytic true function. Turned out for severely ill-posed problem and Sobolev true functions, it just adapts. You don't even need to do much. Okay, so let me give you an idea. So effectively, what we were looking for is for the fractional noise, we're looking for decomposition in IID, sort of normal 0, 1 random variables. The nearest, in terms of the some sort of wavelets, and what we found is decomposition in terms of what they call the fractional wavelets. So it's effectively a fractional differential operator applied to wavelets. And the fraction is h, so which comes from so if you have the fractional noise with Hurst exponent this, so h is the sort of the fractional derivative you apply. It could be positive or negative, right? So, and then the key thing, so for the infinite type of series is here. So these are the fractional wavelets here. This is what for fractional noise. There is a particular expression for these. These are normal 0, 1. And then all the sort of dependence is here in the finite, finite series. So although these z's now are normal independent, but because it's just finite set, it doesn't matter, right? It's just the sort of the parametric part, or penalty for that. And that's pretty much sort of the main thing. If the key assumption is if these fractional wavelets are in the image of A, right? So that's when this method works. Then we can because of this assumption, we can reduce everything to the sequence space, and it's all independent for majority of the coefficients. So here epsilon, the noise not 1/10, but it depends on this Hurst exponent, right? So it's fairly well known. And here the other sort of the wavelet coefficient, the scaling coefficients are not sort of independent between themselves, but they are independent of the wavelet. So that's sort of we call generalized sequence space. And so effectively just the construction sort of effectively that this the assumption is once we construct these fractional wavelets, there exist array spaces that is bi-orthogonal to that, so that we can go back from the sequence space. And then the normalization factor is here effectively will be the level of ill-posedness operating in the wavelet domain. And then again, assumption that we can write f in terms of these new wavelets that we defined, right? So take fractional wavelets and apply the operator. So it's so it works for differential and integral operators, but we haven't studied that in a lot of detail when it works. And now it's sort of we're all in the sequence space. So so this is the sort of just it's a ball of coefficients here. And then we just this sort of a little bit annoying bit that is correlated, but it doesn't make much difference. Again, we have the risk, sort of looking the squared L2 norm in expected value. Sort of just the standard assumptions that the infinite dimension, this is, all exists. So the minimax rate is easy to find in general using project of Eduard Belitz and Boris Levitt. And it's sort of, the tool is effectively need to find the squared expected value of this posterior expectation and then the expectation with respect to data. And the rate is sort of straightforward. We have upper and lower bound. The lower bound, in a sense, the supremum of this over of the f star over this class. So there is this epsilon that comes from the dependence part, the finite dimensional. Then this is the variance term, the bias term. Let me see. Yes, the bias term. And this is sort of the bias from the prior, and that's, I think the Sergei Sagapio and Peter Mathieu called it a saturation term. So it sort of seemed to be all interpretable. And once you plug in whatever the sequences you have, we get the rate. So I think I was just going to give you examples, but effectively, we derived the minimax rate for the fractional Brownian motion, which if you plug in p equals to 0, you recover the direct rate. If you plug in h a half standard rate for the white noise problem, and just we get the optimal contraction rate. There is a little bit of dependence on p and gamma here that we get. When we have the concentration, the minimax rate and the posterior concentration as well for the empirical base that I've presented, right? So the next work I've already started talking about with Volodya. We look at the joint BVM for functionals of F. So that's why we talk about functional, because we certainly can have the BVM for F up to the critical dimension. So if the functional only involve those, then we should have the BVM, which just sort of formulating that. Also, the idea, if we look at the joint distribution, then look at the marginal of F while it's integrating that, we might get a more appropriate coverage, matching the frequencies coverage, because obviously we are shrinking using the Bayesian approach. But we wonder if this using the posterior distribution of kappa will help. Also, Volodya has a whole theory for misspecified. So at the moment I presented this BVM only for correctly specified model for the data, right? So, but Volodya has a whole theory for sort of similar tools, but for misspecified models. So we're looking into that as well. So different variances for different YIs and stuff. And also, we started looking at sort of a general theory for non-commutative inverse problems, so where those operators, for instance, prior and the indirect operators don't commute, again, with Volodya. So this is the, probably not complete, but list of references. Thank you.
Questions?
So how do you work with other type of color noise in terms of how they change the rate?
So,
like Brownian motion is pink noise, if I remember correctly, right?
the bit that in Brownian motion changes the noise is that epsilon, the array. So I think the so there are two things. So let me maybe go back. Sorry, I think it's further. So when you write the fractional motion, the epsilon here, right, in the fractional motion is different, not 1/10, but n to some other power. So that's one way. But the other way is sort of so that'll be here, but the other bit, it will come here. So,
okay.
I mean, it will be here as well. And that bit is responsible for condition, I think, like alpha greater than beta minus half. But the key is here. That you can't change. I mean, it doesn't depend on the prior at all. It's just whatever it is.
Okay, thanks for the speaker again.